you see it?
No, I can't see it yet. Oh, because I don't have the camera on. Now I can see a blank screen.
Okay, let me see.
Oh, there it is. Okay. So it'll come up when I'll switch the thing over in a minute. So this is the wrong slide. These are my slides. Welcome guys. I'm gonna come out from behind the corner. I'm just sorry. I don't want Michael to feel like he's in a corner because he should be interacting with you. And I just like to put myself in a corner because I think it's fun. I'm Mariah. Welcome to the ML Ops meetup. This is the start of our summer series. The summer is only a series because everybody that normally comes is on vacation, so we get a whole new set of faces. We want to thank, where's my next slide? Thank MX for giving us pizza. They usually host this out of their space, which is a little bit nicer and doesn't have this funky mic. But their space is unavailable, so we are here at the Kala/Forge headquarters. So it's fantastic. If you have not already, please join us on Slack. Forge is a great community initiative. It's a great Slack. It's a Slack for all of our meetups. So we do Python and ML Ops and data engineering and Go and Kubernetes, and that's all that we have. A front end meetup that might start soon, engineering leadership, and then all the other side discussions you could possibly think of we have as well. They like to share fun blog posts too. A great Slack group. If you're interested in speaking, we are going to start looking for speakers for the second half of the year. So we will not be meeting next month because next month is like the 24th or 25th. And that's just a holiday in Utah. So we won't have a meetup in July, but we'll be back in August. Always looking for speakers. If you're interested, you can ping me on Slack or LinkedIn or just talk to me. And then, before we turn the time over to our speaker, is anybody hiring? Any jobs? Oh, yeah.
But right now it's just Angular developers.
And your name is Chris Whitehead. He's hiring.
Follow me on LinkedIn because we may have data coming up soon.
Maybe data in the future. Anybody else? Okay.
And we're remote, so you don't have to move to the Midwest. So we're tornadoes.
Cool. And with that, I will let Michael, take it away. I just got to do one quick little switch root thing here, and then I'll go full screen. So you go by, you go big, and now it's full screen. There you go. So you can move your stuff around, and you just need to talk into the mic. That's the only rule. So wherever you're comfortable.
All right, let's see.
Uh-oh. It jostled. Give me a minute. It's just sometimes if you unplug it and replug it back in, your cable will come back. Or I might need to redo the camera. Oh no, Mike, you're back. We're back. Okay, we're good.
Okay.
I'm back. Get more pizza. I'll say it a few more times. Take a box home with you.
Okay, well, thanks everyone for coming. I appreciate you indulging me in my crazy ideas. And so I do have some kind of unique ideas about data engineering. And so I want to share that with you today. Although they're not exactly my ideas, a lot of these ideas are just things that I found that other people smarter than me have already put out there, but they're not super popular. And they're very useful, and they've been proven to be useful in various parts of our industry. So a little bit about me. I am the founder and CTO of a very small dev shop called Onepunch Technologies. And basically what we do is we provide solutions for companies to build their software faster, cheaper, and with better quality. It's it could be consulting, or it could even be actual software development. So I want to first think about, when we're thinking about new solutions, what should new look like with data engineering specifically? And my motivation for wanting to give this talk is this similar motivation for me wanting to start my company, which is I want faster, cheaper, and better quality data engineering. And a big part of that is, well, first,
Just keep going.
okay, what would be a sufficient improvement for them to jump over or to even invest in creating this new technology? So some people, it would be, you just need a slight improvement before they would adopt. And so I'm saying, for me, it needs to be a significant improvement. I want an order of magnitude improvement to what we are currently doing with data engineering. And that's where I'm coming from with this. So another thing to think about is, and I get this question a lot when I talk to people, why should we be thinking about things in the abstract, things that don't exist? Well, first of all, this solution actually does exist. A lot of people do it, and I'll explain more about that later. But we often fall into this thing called the broken window fallacy. I don't know if you've heard of it, but basically in the, oh, you can't really read that, but basically it's a quote from Friedrich Bastiat, and it says, "Your theories stop at what is seen and takes no account of what is unseen." And basically the point of the broken window fallacy is to demonstrate this economic fallacy that a lot of us fall into. And it continues to this day because mainstream economics still leverages this fallacy to try and convince people of certain things. And so the fallacy goes like this. If you have this small town with a shopkeeper in it, and he gets his window broken, some kid comes along, breaks his window, whatever, he then goes to fix the window, and he employs the glazer, and the glazer then turns around and employs the blacksmith. The blacksmith then employs a number of people. There's all this economic activity going around the community. From the outside perspective, we look at that and we see, oh, that's a good thing. There's growth. There's the multiplier effect. There's a lot of people are better off because this window was broken, right? But that's nonsensical. We can spot a part of their fallacy, which is they're focusing on things that we can see, but not what we can't see. What we can see is all the economic activity. But what we don't see is what the shopkeeper lost, what he could have had if he didn't spend the money to go fix the window. So he could have actually employed another person in the community. That would have been a net gain, economically speaking. He could have maybe bought a new suit, is the actual original story. And so we're not considering that he could have had the window plus the suit, or the window plus employing other people. And instead, we're taking him out of the equation and only looking at other people in the community. So as senior level engineers, we should have a good understanding of trade-offs between solutions that we're choosing. But oftentimes what we forget is the solution in our mind's eye, the thing we can't see. We'll look at things that already exist, like that we've done before, or things we see other people doing. But we also need to take into account what we could have had if we didn't invest in those other solutions. So I want to put it out there for what is data engineering? And it's not a gotcha, it's just off the top of your head. What would be a good way to describe what we do, or what you think a data engineer does if that's not what you do? Yeah.
So the art of processing and transforming data across an organization for multiple use cases.
Okay, so the art of transforming and processing data across an organization.
Or storing it.
And storing it. Okay. It's probably what I would have said. Okay. All right. So, so we have in our profession, we kind of mirror these other professions in the world. We're kind of we use them as an analogy for what we do. And so I guess my question is, a lot of times when we think of engineering, we might think of the analogy of someone or two people, like in this photo, which you can't really see, but it's basically two people with a hard hat. They're designing and constructing a building. Or maybe this is a better analogy of a plumber. And so maybe I'll put it out there. I want to get the consensus of the room. Raise your hand if you think that we are more like the first picture, these engineers, or if what we do is more like a plumber. So engineers. Okay, no hands. Plumber. That, I was not expecting that, but yeah, I think it's debatable, honestly. Like there's some things between both of them. So let's dive into that. So let's look at where the words actually come from. So for an engineer, I found this really interesting, that this concept of create comes up in the historical usages of the word, but in two ways. The first way is we construct something, or the engineer is able to construct something, but in the other way, the create means creativity, meaning it has this combination of constructing something unique that is also useful. And then there's other concepts that kept coming up. And one of them was the use of engines of war, because for a long time, that was the meaning of the word engineer, was because what were the engines that they actually worked with? It was engines of war. So for many centuries, that was what an engineer was. Okay, so let's think about a plumber. What are the concepts that derive the meaning of the word plumber? Well, most of it came from a surname, but also it originally was someone who worked in lead. You would smelt lead to be able to connect pipes together. And then it kind of solidified into what we know it as today, where it's just pipes and fittings. Like, even though you don't work with lead a lot, maybe you do, you're a plumber if you just put together pipes and fittings. Okay, so, all right, let's take another crack at the definition of data engineering, because we want to have a good understanding of what we're going to be aspiring to do. And I think this is how I would change that definition you gave earlier, which was already pretty good. I would just tweak it slightly. I would say it's creating an engine or machine that can manipulate data through space and time. And so there's a couple of things here. One, we're sticking with the creativity aspect, both making something that is useful and unique. But the other important part of this is that we are not doing the data manipulation. We are creating the machine that does the data manipulation. And so kind of a silly example that I can't get out of my head now is if you were to like go buy a car and you talk to the salesperson and you say, "Hey, I like this car. I want to look under the hood." And you pop open the hood and you see some person just kind of squished in the car bay. You would be like, well, what is this? And then the salesperson is like, well, the engine doesn't run unless he's in there. So, he's got to blow on the intake. He's got to like unplug this hose once you hit 40 miles an hour and plug it in. Like that, we would not call that an engine. But a lot of what we build is exactly that. It doesn't run unless we have a person there doing those things, sitting in the engine bay. So I think that calls into question either that we are engineers, in fact, or that maybe we're just not very good engineers. So there's another profession that is kind of analogous to what we do. And that's this guy, which is a mechanic. And I thought this was interesting because when you look at the etymology of mechanic, it kind of made me think it was similar to an engineer, which it was for many years. It was because somebody who worked with the machine, it was just different concepts of the same word. So this mechanic is inventive, ingenious, handicraft worker. But I'm gonna stick with like the common vernacular of what we think of what a mechanic is, because we don't really think in terms of like this anymore. A mechanic is somebody who works on the machine, works with the machine, but doesn't construct or design the machine. So engineers are the builders of the machine. Okay, so now I think we also kind of confuse this concept of these different professions because just in terms of just casually talking about them, we might talk about the engineer as if they're kind of at an elevated status because maybe their education is a little bit more. But the interesting thing about all these professions is that there's really a subtle distinction between them because in terms of their education, because they all have to understand physics. You think of plumbing, how your house would be without plumbing, and even plumbing done in the right way. A plumber has to understand physics to the degree that they have to understand the hydrodynamics. They have to understand how pressure and velocity works, because they have to get the right size pipe fitted to the other right size pipe. With a mechanic, it's kind of similar. They have to understand physics to understand what's going on in the engine. But the distinction is that with those two professions, you only have to understand a set amount of physics. But with an engineer, when you're applying it to creativity, the degree to which you understand physics is the degree to which you understand, or the degree to which you can unleash your creativity. Okay, so question is, what would the physics of data engineering be for us? And so let's put out some proposals. Well, language features or understanding languages, that's a good thing. We can't really do our jobs without, understanding. We got to learn a bunch of different languages. Patterns, object-oriented patterns, these repeatable techniques that we can apply over and over again to do, we see other people having success, we can copy those. Reading the manual, that's just something generic to say, hey, like understanding all the other technologies, like the different kinds of data storages, like databases or different messaging queues for transferring data, like Kafka or RabbitMQ. These things would help us unleash our creativity, right? I don't think so. I completely disagree. And this is where you'll see my heretical side, because most people would say that. And if you look at our industry, that's what we focus on. When we do tutorials, when we think about learning data engineering, we'll follow those 3 bullet points. But what I think the real physics of data engineering are category theory, type theory, and proof theory. And it's these things that unleash your creativity. It's these things that help you build the engine. These other things help you operate the engine. There's a very big difference, but this is what everyone's focusing on. And I want to get to focus on these things. And intuitively, you may understand these things, just like you can kind of put your engineer hat on and build something in the physical world without really understanding physics. You can kind of just have this intuitive sense for how the world works. It's the same thing here. I bet that you understand some of these concepts, even if you didn't study them directly. So I'm not saying that, it's not possible to do good work without understanding these, but I am saying that the degree, the same thing with the physical engineering, the degree to which you understand these ideas is the degree to which you can unleash your creativity in creating that engine that will manipulate data. All right, so Let's talk about what we want this engine to look like. And there's a lot of little things that I want to improve, but the three main things that I come across over and over again where I think it would be that huge leap forward are these. First, the domain expert. So the data scientist, and it's not always a data scientist, that it could just be a domain expert. Sometimes it's your problem isn't specific to machine learning or trying to build something that is predictive. Sometimes the domain expert could just be like an internal user or business, someone who understands the business well, right? But they want access to that data. And the problem is that when they play around with the data, they never want to do it in the production system. And why is that? Because our engine sucks usually. They have their own tools and they're just tinkering. And then, so it's similar to the second point where that second bullet point is saying, well, wherever they tinker, it should be isomorphic to our production system. And vice versa. Our production system should be good enough for them to tinker with. And I question if it's a good solution if a domain expert doesn't want to use it in that way. So if we get to that point, that's a tall order, but if we can get there, then I think that's the order of magnitude improvement that we need. And then performance and scalability, it should not matter. And along with this data sources, it shouldn't matter where the data comes from. It shouldn't matter what size the data is. These are unimportant details to the domain expert. They're important details to us as the engineer. We need to deal with it. But the presentation to the domain expert, it should be irrelevant. Okay, so let's talk about current solutions, and I'm going to talk about the compare and contrast Pandas and Spark. And I know there are more data solutions out there, but Pandas and Spark are the go-to solutions. And for different reasons, you'll go to one or the other, but the Venn diagram of both of them covers most of data engineering and how in production systems anyway. And Pandas is generally the best tinkering tool that we use. And if it's not Pandas, maybe it's R, but usually Pandas can be production ready faster than R. So the pros of Pandas, it has a nice API. And these are almost exact opposites. So what's good for Pandas is the exact opposite for Spark. The cons are that Pandas is not scalable, and the memory management is very specific to the needs of small data. And there are hacks that you can do to get around this, but then you sacrifice software engineering principles in order to get Pandas into production. And another downside, actually, I want to go back to here, this domain expert playground. In Pandas, when you get a domain expert to write code in Pandas, it's always terrible. And so it's probably not what we want to be doing. It's not going to be a good engine if they're contributing in that way. And the alternative is to force them to use Spark, which they're usually not very well trained in and are not very good at. And but it's a similar problem where it's not production ready. Okay, but Spark, the opposite of Pandas is that it is really good at scalable computing, distributed concurrent computing, streaming, but it doesn't have that nice API that data scientists like to work with. And and I put both pros and cons are memory management, because while it is good at actually doing things with large amounts of data, it's not very good at telling you when there's a problem with doing things with large amounts of data. And it should be able to, because it has all the information necessary. Okay, so on to the actual solution. And the solution is a DSL. And I don't know how many of you actually raise your hand if you have experience building a DSL. Do you know what a DSL is? Okay, all right, good. So domain-specific language. So I will go into this history a little bit to explain. So a lot of you are probably familiar with the guy on the right. He's Alan Turing. But does anybody know who the guy on the left is? Actually, did anybody know who the guy on the right was without me telling you? Okay, all right, yeah. So the guy on the left is Alonzo Church. And it's very fascinating how he's kind of been forgotten in many corners of our industry. Has anybody heard of functional programming? He's the father of functional programming. Alan Turing is the father of basically everything else that we do. So what happened was in the 1920s, there was a math conference where they wanted to answer this question called the Entscheidungsproblem. That's German for the decision problem. They wanted to understand, or they wanted to find out, could you write an algorithm that if you gave it as inputs a proposition, it would tell you as its output whether or not that proposition was solvable. And actually, there's kind of variations on it where it's whether or not the proposition is true or false, but at least whether it's solvable. And so this is the question they gave out to all these mathematicians. They said, go solve it. And these two guys went to go solve it. And this is where the paper of the Turing machine comes from. And in that paper, Alan Turing describes the halting problem. But what's not known is that Alonzo Church solved the problem too. He actually did it a few months earlier, but it's considered a concurrent work because back then it took longer to communicate. So they were across the pond. Alan Turing is in England and Alonzo Church is in America. And so everybody credits both of them to solving this problem at the same time. But Alan Turing kind of had this more philosophical way of presenting the solution, and his paper kind of made a bigger splash. But they both solved it. And actually what Alan Turing did after he realized that Alonzo Church beat him to it is he said, okay, well then I gotta update my paper with something interesting. And so he demonstrated the compatibility between the Turing machine and lambda calculus, lambda calculus is what Alonzo Church used in order to demonstrate that the answer to this question. And by the way, the answer to the question is no, you can't, because of the halting problem. So, so then what happened was Alonzo Church is working with his lambda calculus, which is supposed to be used as a logic. And somebody finds a logical inconsistency with his logic. So then it can't be used as a logic anymore, because if you have even one inconsistency, it's done. So he goes back to work on it and says, how can I remove this logical inconsistency? And he creates what is called the typed lambda calculus. That typed lambda calculus no longer is Turing complete. So, in case you don't know, so Turing complete means you can compute anything that is computable. I mean, that's not technically what it is, but for all intents and purposes, that's how we treat it. And the halting problem is, well, we don't know if we give, for all inputs to give to a Turing machine, we don't know if that Turing machine will halt. We can't know. The only way to know is to run it. And then even then, if it runs, we don't know if it's running forever or just taking a really long time. But with the simply typed lambda calculus, it's no longer Turing complete. So we lose some power here, and we can no longer say that it can compute anything that is computable. So it's less useful in that sense, but it's more useful in the sense that now it doesn't suffer from the halting problem. Every expression in the simply typed lambda calculus is guaranteed to terminate. So that means that we can analyze our code without running it to make sure it's going to do what we want it to do. And from that is derived from functional programming, but also theorem proving, automatic theorem provers. So if you've heard of languages like Coq, Agda, or Idris, they come from this history. All right, so one more point about this is, okay, so we're talking about domain-specific languages. we're following the same principle here, where typically what we do when we build these engines is we use general purpose languages like C, Python, Scala. Those are general purpose Turing complete languages. They can compute anything that is computable. But a domain specific language is saying, we are going to go back to this idea where we are going to constrain ourselves and make that language much smaller. Like a general purpose programming language is already pretty small compared to a human language, but we're going to make it even smaller, where we're really going to constrict what we can say in this language. And the language is the way that we drive the machine. So going back to the machine that we're creating, the interface to the machine is always language. You can think of it in terms of like it's a REST API. You can think of it in terms of it's a GUI. But all of those are some form of language. Okay, so when we design our domain-specific language, what we are doing is we say we are going to define our grammar, and I say a level above that is actually discovering your grammar. So you can determine what set of things you want in your language. But the best way to determine that is to borrow it from concepts that we already know. And this goes back to category theory, type theory, and proof theory, because there's concepts in logic that are just immutable that we can borrow from there. Okay, so does anyone, okay, have your, has anybody taken a compiler's course or interpreter's course? Or built a compiler or built an interpreter if you didn't go to school? Okay, all right. So this, I think, it's my favorite interview question when I'm interviewing somebody, is to see what they thought about that course. If you're actually able to build things, you should have something interesting to say about that course. Okay, so we're going to do a very quick run through of what you would do in that course in 3 slides. So, and I simplified it so much to fit on 3 slides, but this is not at all how I would define this grammar. I would probably define it using category theory, but this is just a demonstration. Okay, so this is Haskell. And so right-hand side is the data constructor, left-hand side is the type constructor. So what this means is I can construct a data type, bool type, just by writing bool type. I can construct the string type data constructor. It's data, even though it has the word type in it, it's still data. I just call it, just by typing it, it's constructed. This one is constructed by giving it a parameter map. Map is a type of string and type, so it's a recursive data structure. Okay, so are we following so far? It's just very simple definition of the type. All right, so then we have another data constructor, data source, which takes a type, and we'll just represent the data source as a string. So we'll just, maybe it'll be a file, but it could be a more complicated type where it could be a connection to a database, like a SQL connection or whatever database driver you use. It could be a connection to a NoSQL database as well. So then the terms, this is our grammar, essentially. So going back to defining our grammar, this is it. We're constraining ourselves to only be able to speak these things. So, one of the terms is, okay, so we have a Boolean term that carries bool information. We have a string term that carries string information. Int term carries int information. And we have, we want to pull something from a data source, perform some kind of transformation on it. We have a run transform data type, data constructor, that would take the data source and the term. And this is where type theory would come into play, where if you look closely, maybe you guys, maybe someone's already caught it, but we could pass into this term something that doesn't make sense. We could say bool term. So we run a transformation on a data source with true or false, and that does not make sense. What would we do in that situation? So what we would do is we would say, to make the interface nicer for the user to work with, we would add a type checker that would say, we can only construct valid terms. And if you don't, I'll give you a little hint as to make it correct. But I'm not going to accept it unless it's valid, unless it makes sense. Okay, so but what makes sense is if we're going to run a transform, this term has to be one of these two. It has to be drop column, or maybe we want to perform an operation to sum the entire column. Okay. So next slide. All right, so now this is how we speak it into existence. We have our abstract syntax tree and we need to construct it. So at this point, we're writing code, but we're not saying how to do things. We're only saying what to do. We haven't said go fetch it from the data source. We just said declaratively, there is this data source that has this data. And then when we've constructed this data type, okay, well, let's just walk through the data type. So, so if we want to run a transform, we want to drop the second column on the data source. The data source has a certain schema, and that schema is for this file test.csv. And that schema is a record type. So just a normal CSV, a record type would be the name of the column and the type that's in that column. And so, very simple example. Most data projects are way more complicated than this. Like, for example, int type, like almost never would, well, sometimes, but a lot of times the CSV, a column is going to have multiple types in the column. You can encode that. You can say, well, it could be an int type, or it could be a string type, or it could be this other type, or it could be null, right? So that's, so the thing about this is now that we have our engine, we've constructed it, there's another step to actually get it to run. But that's the important distinction between this solution and all the other solutions. Actually, Spark does a little bit of this, it just doesn't do it all the way. Is that now that we've constructed what our engine will do, the what, not the how, we can analyze it. We can look at it as if it's data, and we can determine for ourselves different hows. So that would be this. So I'm leaving out the implementation, doesn't really matter, but all we're doing is we're writing a function to take that. This is just a compiler or an interpreter. So we're just taking our term and converting it into something that we can then run. And so in this case, maybe custom implementation will convert this term into a string that represents C code because we need it to run really fast, or Rust code. This implementation, we could say, okay, well, Pandas is already pretty good. It gets us most of the way there. Just initially, what we really care about is that we get people using this grammar. That's what we really care about. And then we can just let Pandas do the work under the hood until we get back to rewriting Pandas to do it better. And the thing about it is now we get rid of a lot of problems, like the differences between the tinkering and the playground and production, because it's the same if they're using our grammar. We can write an interpreter that does the same thing, or effectively does the same thing as production does. Okay, so that's it. Any questions about these slides in particular? Okay, so I have worked on many data projects, some of them with Spark, some with Pandas, and even some of them using a custom DSL. And I believe that the solution, the order of magnitude leap forward that we're going to get, will come from some form of DSL. And a lot of the DSLs I wrote were even too specific for data engineering, but it isn't inconceivable that a general purpose DSL for data engineering is achievable relatively quickly. And again, there's not more to this pattern. It's these 3 slides. You define your grammar, you can construct your application with this grammar, and then you write your code generation. And I guess I should say, so there's different types of methods for building a DSL. So I'm talking specifically about code generating DSLs, because there's embedded DSLs like Pandas technically is a DSL. It's just an embedded DSL embedded in Python. So it's leveraging Python to be able to get things done. But I'm saying the code generation is the significant detail that we're missing in a lot of these applications. I want to tell a little anecdote of why this pattern is significant as well. So I worked on a Golang project, and I've worked on many Golang projects, but this one in particular, everyone was really excited when we got to move to Golang because it was so much faster than Python. And it was, and in micro benchmarks, Go is really fun and exciting because it's so fast. But then what started to happen is as we built our first we were porting over old code. So we built the initial features, still faster. But as we added more and more features, it started to slow down. And the idea was, oh, okay, well, Go can handle it. Go can iterate, very quickly over things. Well, what was happening was we were writing our code in a modular way. So I don't know if you guys are familiar with this compiler optimization called StreamFusion. But what StreamFusion is you can write 2 different functions to iterate over a list, and the compiler knows how to merge them together to make it iterate over the list only once. So like you would say, I want to iterate over the list and add 2 to each element in the list. And then in another place in your code, you could say, I want to iterate over the list and multiply it by 3. And then you can say, well, I want to use these 2 things together. Iterate over the list. And when you're reading your code, when you're writing your code, it says iterate over, it looks like it's iterating twice. Because you say iterate over with this function, then iterate over it again with this other function. But a decent compiler should be able to spot that and say, we should only have to iterate over the list once. Even though you said to do it twice, we're going to merge it together so that when we iterate over it once, we're going to add 2 and then multiply by 3 because we know that those operations are commutative, right? So, but Go does not have that ability. And so we were sacrificing that performance for modularity. Then we had to go back and get back the performance. We had to remove our modular code and squish it together ourselves. And it became extremely complex. But the thing is, that similar benefit that we get with StreamFusion is what we get with DSLs, because we've constrained ourselves. Now we can do optimizations that we could not otherwise do. And so that is it. That's me. If you have any questions, let me know. If you want to reach out to me and talk more about this, let me know. Yeah, Chris?
Practical application question. So if I had a team in data engineering project, like how would I go about thinking about scoping a DSL? If I say, hey, I'm going to come in first, we're going to build this, it's going to make it faster in the long run.
Okay.
Yeah.
So you start with the grammar. So it's the same kind of design as an API design. It's how do we want to interact with this engine? And so you would approach it much the same way as if you would write a Python library and say, these are the things I want the Python library to do. You just implement it. You just implement it like these 3 slides instead of telling it how to do it. Another thing, if you want to look it up, this is sometimes known as defunctionalization. So this is taking what we would normally term as functions, lifting it up to be able to analyze it as data. That's the distinction, but the design is relatively the same. Yeah.
So I might be thinking about this the wrong way. I have a like the perspective I'm coming from is from chemical engineering.
Mhm.
But it seems to me like when you're constructing a DSL, you can basically add more and more things to it until it becomes a general purpose language.
To be a general purpose language, it needs to be Turing complete.
Right.
And so you can limit, like this is not Turing complete because there's no, like what you would need for it to be Turing complete is recursion. And one thing that we've found out is you don't need, or you can have structural recursion, you don't need general recursion. Structural recursion is saying, okay, if we have a structure, we can iterate over it until the structure is minimized to nothing. General recursion is saying we're gonna keep iterating until a condition is met. As long as you keep that out, you should be able to terminate and you should be able to perform the analysis that you need.
Okay. Then my real question is, how do you define that domain so that you don't just end up making a general purpose language?
Okay. So an interesting thing about, again, where I said I would not define this grammar in this way, I would use category theory. So there's this idea in category theory of representing databases. This is called CQL, is one person who kind of took this idea pretty far. There's a couple others, but CQL is probably the best one at explaining what it's doing. But you're able to represent database schemas as a category. And in category theory, a category can be represented as a graph. And so if we can represent database schemas as a graph, it's really the same as drawing on a whiteboard dots and arrows, and the schema transformation. So a lot of times a query is a schema transformation. Those are functors in category theory. And so how you would go about defining your grammar is, well, if you understood category theory, you could say, those two ideas, the category, schemas as categories, and functors to be able to transform those categories, to go from one category to another. Those two ideas, we can encode all other things using those two things. And so that's what you would call syntactic sugar. Is if you define your base grammar, and if you did it well enough, it should be able to encompass your entire domain. It should be relatively small. And that's actually the beautiful thing about understanding category theory, is it is so small. Like if you look at Haskell, how Haskell is implemented, there's like 9 or so real distinct data structures at the core of Haskell. Like everything else in Haskell is syntactic sugar built upon those 9 things. So if you could imagine, if you had 9 terms, now it's kind of an exaggeration because Haskell has a little bit more, but essentially it can be small. It's just, and then what you do to add syntactic sugar is you can write more of these helper functions to construct the, like it's just that then constructing the term looks kind of ugly. Like that's not what users would want to use, because if you're only working with categories and functors, constructing this would be super long to do like a simple data transformation. So you would add a bunch of sugar, and the sugar would be functions that help construct this in a more meaningful way. So, okay.
So when you were kind of laying out the two problems of Pandas and Spark, I can think of a couple of, I'm sure there's a ton, it seems like there's a ton of people building kind of like Pandas drop-in replacements that are more scalable. But they use the Pandas API just because everybody's so like accustomed to it.
Yes.
A Are any of those capturing the sentiment that you're kind of outlining and proposing, or are
They-
those different altogether?
No, I think you're right. So I think those are making incremental improvements. I don't think they're making the leap forward because it's still leaving out the idea of the analysis of being able to fuse things together. It's still saying those are still implemented in a way that say how to do it, not what to do. So Pandas, even as good as it is, I still don't want Pandas, even if it could handle large data. I don't want it. Like, I want a better solution. But that's not to, okay, and that's not to say that it's a bad decision to go with those. Like, everybody makes these decisions economically for different reasons. So it just depends on your situation. So yeah.
So eventually, how has to be implemented somewhere?
Uh-huh.
Are you saying that's outside of the DSL and it needs to be somewhere where you common DSL?
This is where the how is implemented. So you still have to do it. You have to, but the how in this case is we're going to take the what and we're going to convert it into like C code or Python code using Pandas or Spark code using Scala, right? So you can't get away from that, but you just have so much more flexibility in the how. Yeah.
Is there a bug reduction advantage in this? Like the way like Elm will write your JavaScript for you and you don't get runtime errors?
Yeah. So that's another thing is like Uncle Bob says, the true cost of software is its maintenance. I think that this is what a big part of what makes it cheaper is when we've constrained ourselves already. So it's just like with lambda calculus, the type lambda calculus, he made it impossible to make that logical error. No, you could not write a term that would produce that error. It's the same thing here. We've made it impossible to have certain kinds of errors. And then the other part of it is it's a lot easier to maintain this in one place instead of scattered out all over the place. When we're generating the how and we do it once, that's so much easier to do it once than to do it multiple times. And even across microservices where it's multiple different languages and you can't even test it very well unless, yeah. So anyway, don't get me started on microservices. Okay.
Debugging algorithm, I bet it would be not difficult to debug.
How so?
I'm thinking, I don't know for sure, but if you're trying to say, you're trying to get an inline debugger, for example, and figure out what's happening, it's very hard if there's no stack traces or certain tools available for you to do it, unless you provide it with.
Right. Yeah. Okay. So if you want to write that tooling, but that is true, but the trade-off is that you just do so much less debugging. Like the idea of using a debugger coming from a language where you're in your debugger to a functional language, that is a difficult adjustment, but you do learn how to do it differently. So it's not really that comparable, but
The idea is to not to require debugger.
right, yeah. But I mean, you definitely could build in, it would not be a good idea, but you could build, because you're writing your own language, you could write your own debugger, but you don't need to. So yeah, because you've eliminated, like basically you take what kind of bug would exist and you can prove that you've eliminated that bug. So it's not even possible for them to write that bug. And of course there are certain kinds of bugs that you can't do that with, but for the most part, the need for a debugger is greatly diminished. Yeah.
I guess you have like a language for domain A and a language for domain B. Like, I mean, because I would think of a general purpose language as a language for, say, domains A through Z. And so I'm just wondering how a domain-specific language would interact with like other domain-specific languages. Does that make sense?
Yeah, you don't really do it. But there are ideas for being able to compose different domain-specific languages in this manner. So if you have an ASD, there's different ideas for composing those. I don't think they're very good. You're usually better off just focusing on the one domain. And if you need something, you just add it. So did you have something?
I did. I think I'm actually probably missing a couple of fundamental like understandings here. But you did mention like how an API is kind of like a domain specific language.
Mm-hmm.
So just from my understanding then, and this may be in left field, modern, like a modern REST API, right? You'd start with defining the data models, like in Python, like you might use Pydantic to say, this, I'm gonna receive this kind of data, it's gonna have these attributes, it's gonna be these types. Is that this piece right here that you're showing where you're?
Yeah, that's it.
And then the next step is you write your functions that actually like execute and do something with that data. That's the next step and and then finally, like you write your endpoint, right, that receives your parameters and maybe you have a couple different functions, one that uses, Python and one that uses, C under the hood, depending on what kind of parameters you receive to that REST API endpoint, it'll pick then the underlying function and then it relies on the data model that you've defined. Is that close to what we're covering here, or am I just?
That is, yes. All those things are similar. The difference here is like, and between what you were talking about is, well, when you write your function in your controller to handle that data, that's a function in that language. You can't analyze that function. You can't change that function at runtime. You can't say, oh, I see that we're pulling in a huge data store or a huge data frame, and so I want to do something different with that. You can't say any of that unless you check it at runtime. In this one, we're saying at compile time, we can analyze the very code that we wrote. That's the difference.
Okay.
Yeah.
Okay, so let me see if I can verbalize this thought, but would you say that somebody could like write a paper using, purely symbolic, whatever the high academics use, mathematical, etc. notation, and essentially create a grammar of like a 99 percentile of data functors that are used generally? Does that make sense? Like the idea we want, theoretically, we want things to kind of have this like NASA level static deterministic attributes so we can kind of achieve situations like this, but when I wake up in the morning and start eating my Wheaties, it doesn't really like come into my brain the ambition to like define a grammar that is that big of types and operations.
Yeah, okay.
Could do everything that I can't conceive of in my tiny brain. Does that make sense?
Got it. Okay. So this is where category theory comes in, because category theory simplifies it to these two concepts, a category and a functor. And everything else, all of abstract math can be expressed in terms of those two ideas. And that's why we don't have to enumerate everything. We just have to understand that core fundamental abstract math, and then we can enumerate as we go or as we need it in terms of those things. And one thing you said that kind of in terms of papers, when somebody defines a language, they will use Backus-Naur form, and Haskell imitates Backus-Naur form pretty closely. So but I guess that wasn't your question, but you just made me think of it. So yeah.
Wondering, I mean, the functional languages have been around, it's more about the functional languages than DSLs, right?
Mhm.
I'm just wondering if it's, the language has been around for a while, but are they getting more traction now?
I don't think so.
Okay.
So yeah, I don't think it's necessarily. I don't think it's necessary to be successful in data engineering. I think the functional. Okay, so my opinion.
In general.
Yeah, so my opinion is that the functional languages are really good at building other languages. And so, but you could build a DSL in any language. But I just think that the functional languages do it better and you'll have an easier time doing it there.
Well, it also complex the code so much. That
Right.
A lot of telecom providers will use Haskell and such functional languages as well.
Yeah, so one thing that I've done before is writing a DSL that wasn't specific to data engineering in Haskell. I actually got better performance in Haskell than I did in C. And actually, there was another attempt to write it in Go. We got better performance in Haskell than in Go. And the reason why, even though Haskell, if Haskell was just, if we had written them the same, if Haskell was just doing the how, the same way that Go was doing the how, or C, Haskell would have lost. And it would have lost by like times 3 or 4. But the reason why Haskell was able to win was because we didn't write it in the same way that you would typically write it in Go. We wrote a DSL, we performed some optimizations, we did some pre-planning for how this execution was going to go. It wasn't a compiler, it was still an interpreter, but even that interpreter was able to execute that code in a more efficient way than the competing languages. So there's still, I think there still is benefit. I'm sad to see that it's not as popular as it is, because people will look at these languages and say, oh, it's not fast, I want to go after what's fast. But it ends up being fast if you do this technique. So. Okay, I think we're done with questions.